Uniform circular motion. Now, what is uniform circular motion? It is a motion in a circle at a constant speed. It is important to understand that the speed is constant, but the velocity is not. That's because the direction is changing. So, the speed is constant, but its velocity is changing. So that if the velocity is changing, then there must be an acceleration as well. So before going over the acceleration and force associated with uniform circular motion, we will start with some definitions. First, we define the arc length. This distance along the circle is given by S, and that distance S, or the arc length, is equal to radius times the angle. So S is equal to radius times theta. It's important that this theta must be in radians. Now you cannot use degrees here. This equation holds only when theta is in radians. Then the average angular speed is given by this Greek letter omega, and this bar represents the average value. So the average angular speed is given by delta theta divided by delta t. So that's basically angular displacement. This delta theta is the change in angle, or the angular displacement divided by time. The units of omega is radians per second. Now let's look at the relationship between the regular speed and the angular speed, and how we can relate those to the period of the motion. This is how the angular speed and the regular speed are related. The speed v is equal to radius times the angular speed. And also we can show that the speed v is equal to 2 pi r over t. T is the period. Period means the time required to complete one full circle. So it's like speed is equal to distance, which is 2 pi r, divided by time, which is the period. So that's why v is equal to 2 pi r over t. Now let's look at the acceleration. We use this as our acceleration. This is called the centripetal acceleration, and its value is given by v squared over r. If the speed is v and the radius of the circle is r, the centripetal acceleration is v squared over r. So for any circular motion, this is the only equation that tells you the acceleration. You cannot use the regular kinematic equations and find the acceleration for a circular motion. And once we have the acceleration, we can find the force. We call that the centripetal force, which is given by mv squared over r, or mass times the acceleration, and it becomes mv squared over r. And this force is also pointed toward the center of the circle. Now we will go over some examples. The first example is an object in a uniform circular motion moves at 16 meters per second in a circular path of radius 2.4 meters. Find the period and the angular speed of the object. Find the centripetal force required to maintain the motion. Mass of the object is 0.5 kilograms. So the first question is find the period and the angular speed of the object. So we have the speed and we have the radius. So we can use one of the equations we discussed at the beginning. V equals 16 meters per second and the radius is 2.4 meters. Mass equals to 0.5 kilograms. So the angular speed v is given by speed divided by radius, 16 over 2.4. So that's 6.67 radians per second. To find the period, we can use the equation v equals 2 pi r over t, and solving this equation for t gives us t equals 2 pi r over v. So plugging the radius and the velocity, it gives us 0.94 seconds. That's the period. Part B, to find the force, we use the equation Fc equals mv squared over r. Mass is 0.5 kilograms and velocity 16 meters per second. The radius is 2.4 meters, and that gives us 53.3 newtons. So that's the centripetal force. That's the force in the direction of the center. The second question, circular motion in a horizontal plane. The diagram shows that the object is rotating in a circle which is in a horizontal plane, and the object is tied to some point above that plane, so there is a tension in that rope. But the radius of the motion, radius of the circle, is not the length of the rope, so that's different. So let's consider that radius of the circle is r, but the length of the rope is l, and assume that the radius is given as 0.4 meters and the mass of the object is 2.2 kilograms and the length of the rope is 1 meter. The first question is find the tension of the rope, and the second question is find the speed and the acceleration of the object. So to find the tension, we need to look at the free body diagram. So this is the free body diagram. We have tension at an angle theta. We don't know theta at this point. We need to find that, and then the other force is weight, which is mg. So these are the two forces acting on the object. So first thing is we need to find theta. Without knowing theta, we cannot find the components of the forces. We can use this triangle. This theta is same as that theta. And also we know this length is the length of the rope, which is L. And this is the opposite side of the triangle. That's the radius, which is R. So we can write sine theta, which is R divided by L. So it's 0.4 divided by 1. So that gives us theta, which is sine inverse 0.4. It's about 23.6 degrees. Once we have the angle, we can consider x and y directions and apply Newton's second law. In the y direction, there is no motion because the object is rotating in the horizontal direction. So in the vertical direction, there is no motion, no acceleration. So we can say the vertical component t cosine theta minus mg equals to 0. That gives us t equals mg over cosine theta. By plugging the values, it becomes 23.5 newtons. Then considering the x direction, we know the acceleration, which is given by v squared over r and is pointed toward the center of the circle. But we also know that the acceleration in the x direction is sigma fx over m. Sigma fx is there is only one force in the x direction, so that's t sine theta. So t sine theta over m. Now we can equate these two, and it gives us v squared over r equals to t sine theta over m, and that gives us t mg over cosine theta. By equating these two, we get v squared over r equals t sine theta over m. But in the previous slide, we found t, which is mg over cosine theta. Then I'm going to plug this t into the equation, and which gives us v squared over r equals to mg over cosine theta times sine theta over m. M cancels from the equation, and sine theta over cosine theta is tan theta. So v squared over r becomes g tan theta. And by solving this equation for v, gives us v equals square root of rg tan theta. Now we can substitute the values. R equals 0.4, g equals 9.8 times tan 23.6, which gives us v equals 1.3 meters per second. Once we have the speed, we can find the acceleration, which is v squared over r. So it's 1.3 squared over 0.4, and that's 4.2 meters per second squared. The next question is about banked curves. The motion on a banked curve is also a circular motion. So it says the radius of a banked curve is 0.8 kilometers. The curve is banked at a 20-degree angle. Find the maximum speed a car can travel without relying on friction. Okay, so what happens here is, if the car tries to go faster than this value, it will skid. So this is the maximum speed that the car can travel on this road banked road without skidding, ignoring friction, without considering friction. So now let's look at the free body diagram and see how we can answer this question. The car has its weight mg pointed down, and then there is a normal force Fn which is perpendicular to the ramp. So that's in that direction. Let's assume that this is our x direction and that's our y direction. So we can consider x and y separately and find out the accelerations. In the y direction there is no acceleration, obviously, because the car doesn't move up and down, but the only motion is in the x direction, which is a circular motion. Again, it's a horizontal circular motion. So let's start with the x direction. Since it's a circular motion, the net force in the x direction must be the centripetal force, so which is sigma fx. So in this case, the only force in the x direction is Fn sine theta. So the centripetal force Fc is Fn sine theta. But if you consider the y direction, you can see that this Fn cosine theta, which is in the upward direction, must be equal to mg, because the acceleration is 0. So Fn cosine theta equals to mg, and that gives us Fn, which is mg over cosine theta. Now we can plug this into this first equation, which gives us Fc equals to mg cosine theta times sine theta. So that's equal to mg tan theta. So Fc equals to mg tan theta. But we also know that since this is a circular motion, Fc is mv squared over r. By equating these two, we get the velocity v equals to square root of rg tan theta. So now we can substitute the values, which gives us velocity equals to 53.4 meters per second. Another example for a circular motion is the satellite motion. Some satellites are in circular orbit, so we can consider the motion of a satellite which is in a circular orbit. So this says a satellite is in a circular orbit around Earth. The orbit is 300 kilometers above the surface of the Earth. What is the speed of the satellite? Average radius of the Earth is 6.7 times 10 to the 6 meters. So that's the radius. What we need here is actually the distance between the center of mass of the Earth and the central mass of the satellite, which is not the radius of the Earth, but is the radius of the Earth plus the height to the satellite from the surface of the Earth. So the total distance r is the radius of the Earth plus the height. So that's 6.7 times 10 to the 6 plus 300 kilometers, that's 300,000 meters. So the total distance r, or the radius of the actual radius of the satellite's orbit, is 7 times 10 to the 6 meters. Considering the forces acted on the satellite, the only force is mg, or the weight of the satellite. So centripetal force must be this force, because this is the force toward the center. So Fc is equal to mg, but we also know that that's equal to mv squared over r. So that gives us g equals v squared over r. So ov squared equals to rg. It appears like at this point we can find v, because we know r, and we tend to think that this g is 9.8. But that's not the case, because at this altitude g is not 9.8. It changes. It's lower than 9.8 at a 300 kilometer altitude. So we need to find g, acceleration due to gravity, at this height. That value is given by Newton's law of universal gravitation. We obtain that equation, g equals capital G me divided by r squared. This big G is a constant. Me is the mass of the Earth, and r squared is the distance between the two objects, or distance between the center of the Earth and the center of the G equals G me over r squared. G is a constant, and ME is the mass of the earth, and R is the distance between the central mass of the earth and the central mass of the object. By substituting the value of G, we get V squared equals to R GME divided by R squared. So 1R cancels here. So GME over R. So V equals to square root of GME over R. So G equals to 6.67 times 10 to the negative 11 newtons meter squared per kilogram squared. And the mass of the earth is 5.98 times 10 to the 24 kilograms. The radius is 7 times 10 to the 6 meters. So by plugging those values, we get V equals 7,550 meters per second.